My name is Timothy Kiris. I'm a graduate student in computer science at New York University. My co-authors are Mohammed Junaid Farouk and Kwanyan Zhu of the Department of Electrical and Computer Engineering. And our topic is the modeling and assessment of IoT supply chain security risks, the role of structural and parametric uncertainties. What we're going to look at in general is how to do a system-level risk analysis, but keeping in mind and looking at the different kinds of uncertainties that process involves. So first, some context. We might say that cybersecurity has become a higher dimension problem. We illustrate this with the diagram on the right. The horizontal dimension shows an IoT network, and we note that IoT adoption in critical infrastructure enables new targets. The vertical dimension shows a supply chain, and we note that supply chains contain implicit attack vectors. An attack may involve either or both of these dimensions, and so risk analysis and mitigation must consider both as well. Our topic considers priorities in model development. So understanding the possible threats posed by suppliers requires modeling component relationships. Modeling this is complex and involves uncertainties that will affect the accuracy of the model. In general, we can allocate resources to improve the accuracy, but those resources will always be limited. So which kinds of uncertainties should be given the highest priority? So just to frame what we're going to talk about for the rest of the presentation, what we're looking at is a foundational model to do risk analysis at a system level involving suppliers. However, we're also looking at the issues of uncertainties that involve this model and how to work with those uncertainties. So next, what we're going to do is look at the system model we've developed through a couple examples. What you'll notice at first is that it's a graph-based model. We have nodes and edges. We have component nodes and supplier nodes. The component nodes are connected to each other, and they also possess a logic function which explains how the component is related to its dependencies in the system. The basic idea being that a component has a security property, and that property depends on the security properties of its dependencies. So if those dependencies were to be compromised, then the component would also be compromised. You may note a resemblance here to a fault or attack tree, and there is a close resemblance of the model with the addition of suppliers. And so every system model is going to contain an attack goal, which is at the top, and that attack goal will be sort of capture what the goal of this particular model is designed to analyze. In this case, we have a simple attack against component A. Now, there are a number of different kinds of attacks. The first would be a direct attack against the component. Here we have an attack against component B. And this is typically what we'd have in mind when we think of a security incident, a breach, a compromise. We also have a supplier attack. Here, it's a supplier attack on supplier B. And you could consider this as a malicious supplier or a supplier that's been compromised. Either way, the assumption of our model is that if supplier B has been compromised or is malicious, then the components that it supplies are also compromised. Here's another example of a supplier attack. This case, the supplier of A has been attacked, and component A is now insecure, and that leads to the attack goal being reached. We also have indirect attacks. These would be attacks that compromise the dependencies of a component. What's illustrated here is an attack on supplier B and component C. And together, the attack sort of propagates through the system, leading to the security failure of component A, and that is the attack goal has been reached. What we've noticed is that attacks can be listed as a set of nodes. And we introduce here some terminology. A cut set is a set of nodes such that the attack goal is accomplished if every node in the cut set is compromised. A minimal cut set is a cut set with redundant nodes removed. You can think of this as the smallest possible version of that cut set. It's necessary to use minimal cut sets in order for some of the calculations to work out. A set of minimal cut sets is the set of all minimal cut sets for a given system. When we have the set of minimal cut sets, we know all of the different ways that the attack goal can be reached, given our system model. It's a lot of information. It's also very powerful. In this particular small, very, very small example, we haven't even listed all the cut sets, but some of them are down here. Component C and supplier B, supplier A, supplier B and supplier C, etc. Again, these are all of the different ways that the attack goal can be reached. If we have the minimal cut sets for a system, and if we have probability values that correspond to the probability that any particular node is compromised, then we can combine these two things to produce a risk value for the system. The probability of a particular minimal cut set being fully accomplished is the probability that all nodes in the cut set are compromised. If at least one minimal cut set is fully accomplished, then the attack goal has been reached. So in general, then risk would be the probability that at least one minimal cut set is fully accomplished. I'm going to rephrase this here as risk is the probability that it is not the case that none of the cut sets have been fully accomplished. It's a bit of a mouthful, but it helps to mirror the formula below. So we have, if we're given minimal cut sets and a vector of probabilities, then we can combine these two to produce a risk calculation for the system. George Box said, all models are wrong, some models are useful. You may be thinking that this sort of modeling involves a lot of information. We need to know all of the components, we need to know how they're related, their security properties, how they depend on each other, which suppliers are involved. And in addition, we have to have probability values for the failure of any of these and all of these entities. It's a lot of information to get right. So given the fact that our modeling process is going to have resource constraints, how can we make the model more useful? And one answer to that question would be to address the most critical kinds of uncertainty first. So we divide uncertainties into two general categories. The first would be a structural uncertainty. And that looks at the question, have we accurately understood the security implications of a particular component or supplier? The second category will be parametric uncertainties. And this deals with whether we've got the probability values correct. In this study, our general procedure is to create a model, including cut sets and probabilities, and assess risk. Then we go through all of the different kinds of uncertainty that we've thought of, perturb the model to create a hypothetical mistake of that kind of uncertainty, and assess risk, and repeat many times and across all different kinds of uncertainties. At the end of this, we should have some information about which kinds of uncertainties produce the strongest and most largest change in probability, change in risk at the end of the day. Those would be the kinds of uncertainties that we want to prioritize. So in order to do this, we've created a simple example. Here it's shown in our figure here of system graph. It's got a nice tree shape. It's 25 nodes. There's a variety of and or logic kind of scattered throughout them. So this is the base case. This is the accurate model. If we had a perfect knowledge of a system, let's just suppose that this is the information that we would get. This is sort of the reality. There's a lot of cut sets in this system. There's 53 minimal cut sets. I've listed some of them here on the right. Now, we also have to provide probability values for the compromise of each node. And for the base case, we just set them as all of them as the probability is 0.05. So using our risk calculation procedure, we come up with a systemic risk of 40% in this system. And now what we're going to do, this again is the base case, the accurate model. So what we're going to do is look at some other versions of this system that are not accurate and just see which kinds of versions are the farthest from this ground truth. First, we have the case of a discrete logic error. This means is that when assigning the logic type to a node, we just got it flipped, got it backwards. Illustrate this with an example. Here, component B has been labeled as OR instead of AND. What this means in this case is that node B is more vulnerable, it's more permissive. To compromise node B, you only have to compromise one of its dependency paths instead of all of them. Now on the right, we have a chart showing on the horizontal axis, we have every node in the system. And the vertical axis shows the change in risk when we apply this kind of error to that node. What you'll notice immediately is that nodes that are to the left, these are nodes that are higher up in our system, closer to the attack goal. When we get the logic wrong of these nodes, we are farther from, we have much larger change in risk. When we move to the nodes in the middle of the system, it gets smaller. And of course, leaf nodes here wouldn't have any effect because they have no predecessors. This is a pattern we'll see throughout many of the examples, that nodes higher up in the system are more important. In case 2, we look at the omission of a node. So when doing this, trying to model the system, just a whole node was missed. It was a whole subsystem in the system was just overlooked somehow. In this case, node C was overlooked. That's a very high level node. So what's left is this is the view of the system that would be assessed. On the right, we have a similar graph. We have nodes labeled on the horizontal axis and the risk on the vertical axis. And you see for node C, yeah, it makes sense. So if you take out node C, the risk is going to go down quite a bit. There's fewer ways for the attack to proceed. In reality, this probably would be flipped, so it would be a increased risk if you missed a node. But that's just an artifact of the way we're presenting this. In case 3, we have an error in edge placement. So this involves you've identified the component properly, you've identified its logic type properly, but its location in the system has been misassessed. So for example, our base case had an edge between D and B, but in this error, we show D being a predecessor of E. We don't have a nice chart for this one because there's so many different combinations of errors and edge placements. But you can see in this particular case, there's a slight increase in risk. And case 4 looks at our second type of uncertainty, which is parametric uncertainty, or an error in probability estimate. So we just suppose that all of the estimated probabilities are higher than estimated. Say we were kind of across the board optimistic about our probability errors. So we plot this on the right, where we have sort of a probability error on the horizontal axis. And this is, so in addition to the base is always 0.05. But if we add 100% of that, then that would be represented on the right of the graph. The vertical, again, shows the change in risk. And you see it's a nice linear relationship. So when all the nodes' risk goes up, then the system risk goes up in a linear way. It's happening to all the nodes at the same time. So that's why it's linear. It's a steady and problematic increase in risk. what we'd like to highlight is if we compare the parametric uncertainty and one example of a structural uncertainty. So suppose we look at the example of a discrete error in node B. This is the one we showed before. So one particular node, we accidentally modeled it as more secure than it really is. And so risk goes up by about 0.15. So we want to ask the question is what kind of error rate in our probabilities would we have to get in order to have that level of risk change in the end? So we just go over here to this chart and find 0.14, 0.15. Well, that's about a 50% error rate in the probability. So again, in order to have an assessed risk of equivalent to missing logic on node B, we'd have to be wrong by a factor of 50% in all of the probability errors. This should highlight is that a high-level structural error can be a really big, can have a really big effect in the change in risk, and even compared to a very large across-the-board probability error. So in conclusion, we've seen that assessing supply chain risk requires understanding how the security attributes of components are interrelated, but modeling this complexity is subject to uncertainties that will affect the accuracy of the resulting risk assessment. Using case studies, we can better understand the limits of modeling practices and prioritize the most critical questions. This study suggests two best practices. The first is height over depth. Components closer to the attack goal are much more critical to assess accurately than those further away. The second is structure over magnitude. And if we say that the magnitude of probabilities are in the ballpark of being accurate, then inaccurate structural assumptions likely pose greater risks. That brings us to the conclusion of this presentation. Thanks for your attention, and I'd be happy to answer any questions.
Thank you, Tim. I enjoyed that presentation. I'm going to give some other people a chance to type some in, but I have one right away. My first question is, you used parametric estimates. I was wondering if you would consider also using non-parametric, and if you did, would you weight by maybe like traffic flow, or would you consider weighting by that in future work, or perhaps by some other metric? Or data type, I should say?
Yeah, that's a good question. So this study was sort of looking at a foundational question and sort of almost trying to get behind the modeling practice and do some assessment of how to deal with the uncertainties. So we kept the model pretty simple because any more complexities would still have the same fundamental question of where is the system information coming from, and how does it affect the accuracy of the end result. But there would be a lot of different strategies to increase the sophistication of a model like this. I think, looking at the traffic would be a really good way to say, just in general, which nodes would be more likely to be targeted. So I think that would be a good choice. But I think there would be many different ways to improve the sophistication. And we'd hope that any of them would, none of them would be able to go around this fundamental problem of where is the basic input coming in. And I think that's an issue in security that is often encountered, but also something that I think people are used to working with. And so hope that this kind of modeling can be part of that also.
Okay. Kind of strikes me that much of what you're doing here we've seen done in other industries, so I have high hopes for it. I'll say that. I suspect there might be some other, are there any other audience questions? I don't want to dominate the time here. Okay, well then I'm going to ask you one more. So I kind of alluded that this reminds me a lot of work that's done in reliability. So how would you apply this to resilience, the ability, you know, the recovering aspects of resilience?
Yeah, so I think one of the key things in developing resilience is the ability to measure the results by some kind of simulation process or modeling process that can be really helpful in getting the results in practice. And so we think this kind of model can be helpful in assessing what is the net gain in reduction in risk, for example, by adding certain kinds of redundancy or adding certain mechanisms. It's again very similar to attack trees, only with the addition of suppliers. And so you can use that information then to assess different strategies for resilience would be sort of the idea that we'd be heading in.
Okay. Oh, goody, here comes a question. Is there any plan to apply, this is from Joseph Barnes, is there any plan to apply this model to a known supply chain compromise to see if it's correctly predicted what was targeted by the attacker, sorry.
Yeah, we'd be interested in using real data instead of an example like this. I think it would be helpful to continue to validate or improve the model in different ways. The key points again will be, though, to what extent are the parameters, the structure of the model, matching the reality of the supply chain and the system in question, and the results can't be better than the accuracy of those input parameters. So that's again, that's been the topic here.
Well, thank you, Tim. That was very enjoyable.